G'day YouTube, JB from Oz again. So you'll recall in my last video we've got the Arduino set up with two positional sensors and an LCD screen, and the purpose of that was to be able to do our initial setup for a spindle tachometer for the AL960B lathe. What I'm using here is an Arduino, which is the microprocessor at the underside of this board on top of it, which is called a shield. This particular shield adapts the Arduino's pins for a 3D printer, and rep-wrap style 3D printers are configured in such a way that you have stepper control. There's 5 stepper outputs, you have some end stop inputs and outputs, and your various other things like your thermistors for temperature sense, and also some external drives that you can control. There's also main switching for your extruder heater, your bed heater, and I forget what the other item is, probably an LED or a light or a fan or something like that, I seem to recall. You can put a 12 volt input from a main switching power supply. You've got an ability to add a single supply through to the Arduino. There's a second shield on this board, which is an LCD breakout board, which I've got connected to a 128 by 64 character LCD matrix. And the particular piece of software that I've got running on the Arduino at the moment is my spindle tacho software from the other night. So when I plug in the Arduino, the software boots, and we end up in our ready state for the spindle tack program that I loaded up. So we get the idle state ready to measure, we get an indication of RPM. These two other values below are the counters, or at least the time counter, for the last trigger of each of these two optical sensors. So I'll just see if I can trigger, let's see what I've got that I can trigger that with. That's a forward direction. And then this is our reverse direction. So, in order to achieve that, we're using 2 of the sense input pins on the ramps, and we have behind that a voltage plus 5 volts and a ground supply. Moving on to our linear encoder scales, what we worked out yesterday is we've got this Hitachi voltage comparator. Alright, thanks to the joy of the internet, we've been able to find the data sheet for that chip, which is HA17339. It's a voltage comparator. We've also got the chip schematic, the notch in the pin and the notch in the pin, we can see. So we know the orientation, and we know that we've got output 1, 2, 3, 4, we've got our supply in, we've got our ground in. The other inputs are inputs to the voltage comparator. Typically a voltage comparator like this could be used to switch on and off once an input voltage crosses a threshold voltage. So my guess will be that the potentiometer in there is being used to set the threshold voltage, and we've got a 5-pin header there, so my guess is that that will probably be used to set the device while you're in test mode. Make sure you've got your voltages set right. So what I'm now going to do is I'm going to trace the 4 pins that I've dotted, which is the V1, 2, 3, 4, to see which, if any of those, connect up to the pin headers. The ground, which is the big white bar, should connect to our white lead. The V+, VCC, should be the one just underneath the ground there. I'll use the tests to tell me which pin is which. I'll also then use the same test so I know what pin outs are, depending if I go with this particular connector or I chop the cable and put a different connector on. So let's see what we got. So what we talked about earlier is we've got a voltage supply, we've got a ground, we've got some inputs and some comparating happening, and then we have an output. So we're only seeing outputs 1, 2 and 3 connected through on the cable. So typically you would have 2 outputs, such as we have here, triggered in order to be able to sense a direction. The third possibly is to indicate a start or an absolute indicator position. Now it might be such that when the travel goes off the end of the scale, being that we have a row of 4 sensors, we can pick off a point where that third input reads nothing, and then once it starts to read is the very first pickup on the optical sensor. So my next step is to do some debugging around that. So what I'll do is show you what I've done here. A bit of hot melt glue and some breakout pins so that I can tap into this cable, and what I'm looking at here is, according to my output diagram and my orientation, the ground is my black cable, my V2 is my brown cable, my VCC is my red, my V1 is my orange, and my V2 is my yellow. So if I provide power to the circuit using these 2, I should be able to use these other 3 pins to detect a signal from the optical slide, the DRO. And essentially what I'll do is I'll set up an interrupt reading when one of these changes state, and then display or record the state of the other 2, and see if that changes as we move forward or as we move backwards. And quite what happens, I'm expecting we'll see a high value, a low value, or a matching value and a low value, and a matching value and a high value, depending on the direction of travel. If say V1 and V3 we're reading in the same absolute position, we'd expect to get the same reading, and if V1 and V2 were 90 degrees out of phase, we'd expect to get the opposite reading. So that when we travel off the end, if we got no reading at all on V1, but we had a reading on V3, that would be an indication that the V1 sensor is off the end of the scale, but the V3 is still on the end of the scale. And so by detecting that rising edge, we can essentially pick up when we go over that point. That's all pretty long-winded. Let me try and give you an example by wiring this up and seeing what we end up with by using these 3 as inputs on our sense pins, using this as our power supply. Bring you back. So we want to test our wiring is correct as a first test. So we'll bring our Arduino out the way and bring our assembly in alongside our wiring. So what we're essentially going to do is have a pin connected up here. So a red pin should essentially connect to a red pin there and not to any of the other pins, which is great. Now we want to check our black pin. So this should be connected to our ground, which is also a black pin there, which is great, and nothing else. Now we have our other input sensors. We have our brown, which we have said is our V2, which should be this pin here, and that pin there, which it is. Then we have our orange, which should be our V1, which is that pin there, and our yellow, which should be our V2. Okay, so brown is our V3, not our V2. Alright, so now we've verified the wiring on our cables, and I'm fairly confident that with our hot melt glue jury rig here, we're going to be fairly safe. We're not going to short anything out. What I want to do next is jump in where we currently got our end stops and our inputs connected. Good on you, Johnny. And I'm going to plug in these. We've got our plus 5 volts and our ground. Okay, so we can now check that we've got power to our chip over here. And I'm showing 5 volts. Alright, so we've got 5 volts, and now we have the opportunity to connect 2 sensors into our existing coded inputs on the controller. So I'm going to go with V1 and V2. So essentially what we've got is interrupts which are going to occur when V1 triggers, and V1 is our orange. So I'm going to start with our orange. So essentially, hey, look at that. Each time that triggers, we're getting a read. Look at that. Alright. So, what do we want to do? We're going to see if V2 triggers, which is our yellow. So if I plug yellow alongside, hey, they're both triggering. Alright, so hey, check that out. Fancy that, eh? We have our read from our scales. Now, what I want to do is take our third input, alright, so I'm now going to write a slightly different piece of code to see if I can do, actually, no, let's do this. Let's see if our third input actually also provides a value. Hey, check that. So there's a point that our third value fires at. Check that out. So that means we've got a datum in our scale somewhere around here, which looks to be about halfway. Doesn't fire anywhere along the trip. Just there. Okay, that's beautiful. Alright, so our third sense pin is our datum 0, so that regardless of any other information, there's a marking on our scale which, when it triggers, gives us our 0. So we could essentially say 0 plus and 0 minus from this location. So the next things we need to determine are the pulses. How do we count the pulses? What the pulse means in terms of a distance, which I think what we're saying on these scales is they're 5 micron per pulse. There's a value somewhere as far as resolution. So we've got a 450mm length, we've got a 5 micron resolution. So if that's the case, we should see a trigger at 0, an increment or a decrement depending on which direction we're going, and a 0 to reset to 0. Brilliant. Haha. I'll write some code, I'll come back. Okay. Well, after a little bit of jiggery pokery, I'm having a little bit of problems with pins D14 and D15 on the Arduino board, so it might be a faulty board or a faulty ramps adjuster, but I'm happy to report some success. So if I reset the device, essentially powering it on, I've got a reading of 0, and I've got an interrupt set up on the first, the input 1, so that on the rising pin 1, we're going to take a reading of what pin 2 is at, i.e. so it's like A and B. So if A is rising, is B falling or rising? And that'll tell us the direction. Based on the direction, I'm incrementing or decrementing the absolute position. The third one is a reset. So at the point where I'm triggering the A pin, I'm checking to see if the reset pin is also up. If it is, I'm then resetting the counter. So as I move the scale, I'm getting incremental and decremental values and negative values. And 0. So the next thing is to see how does that relate to the real world, and I've got a scale on here, and I'm going to move the scale 10mm to the left to about there. It's about 10mm. Okay, so 10,000 microns, 10mm. So I've got it calibrated that for each run through the cycle on the upward stroke of the A pin, we've got 20 microns movement. Now the scales are a 5 micron resolution, which indicate that with a little bit more accuracy in the programming, it should be possible to increase the resolution down to 5 microns. And I've read somewhere in my paperwork on the interwebs that the Arduino is going to struggle to do much in the way of high-speed resolution. Like for instance, if I move away quickly and then come back, I've lost some steps. So it's not keeping up with rapid transfers. I've got a reset happening at 0 again. So I can see if I go there, come away, and come back in, if I'm not traveling fast, it's pretty close to where it should be. But as soon as we get any fast traversing, we're just running out of CPU cycles. Now I'm using a digital read, not a fast digital read, so I've got a way to solve that. But for tonight, I think we've got a glass scale input plugged into our circuit and providing us with a calibrated, essentially X position. So I'm pretty happy with that. So, things I found out is we do have on this scale a reset on the positive travel think it's a 425, so we should get to 215 or something. Okay, 265 in the positive direction. Just running it down to see if I've made any jump steps. Okay, that seems fairly reasonable. And how far have we got on the reverse direction? So we've got, if this is a 450mm scale, we've got 460 odd millimeters, so it's just a little bit outside of that. So we've definitely got our working range of 450 millimeters. We've got 200 millimeters on one side, or 208, and 265 on the other side, with our center in the middle. So with appropriate location scale and running through that 0 point, we essentially don't need end stops to accurately maintain position, provided I can deal with the digital read fast process. Now, as far as the code, let's have a quick look at it. So we've got our initializer for the LCD screen. I'm using pin 3 and pin 2 as our A and B inputs, and I'm using pin 18 as my reset. Setting up some variables just as troubleshooting, debugging. Absolute position in microns. We've got our draw command, which essentially prints our screen. So we've got our line which has the value, our micron value, and then the text microns. And then we've got the last time XA triggers, last time XB triggers, and last time X reset triggers. At the moment, the last two values aren't being used. I'll do my pin definition. XA input is an input with a pull-up resistor, XB is an input with a pull-up, and reset is an input with a pull-up. We're setting our interrupt on the XA such that when it's rising, we trigger count. We could have this set so that it's rising or falling, so anytime there's a change on A, we can check B. So if A was falling, we would look for the opposite result on B to detect the direction, whereas at the moment we're wanting A high, rising, B falling. So higher accuracy, we just maybe need a bit more computation or a second test. Basically our main functional loop, just draw the page, and our interrupt loop. If we trigger, record the time, we're doing a read. If the reset is high, we're resetting our position. Otherwise, if our B input's low, we're subtracting 20 microns, otherwise we're adding 20 microns. And these other two interrupts are doing nothing. So essentially this is the guts. Whenever A triggers, is B positive or negative? So we're incrementing or decrementing the position. If A triggers and our reset is there, we're setting our position to 0. And that works, man. Thanks for watching. And as for the previous video, I'm really trying to get to the 1,000 subscribers by 18th of February. So anything you can do to help, either subscribing yourself or encouraging other people to subscribe, would be greatly appreciated. Thanks very much again. Bye.